We're going to start now to look at operational properties of the Laplace transform that add to its versatility as a tool for the work that we're doing with it. First, we're going to look at the first translation theorem, also known as a first shifting theorem. If uppercase f of s is the Laplace transform for lowercase f of t, and a is any real number, then the Laplace transform of e to the at times f of t is the Laplace transform of f with an argument of s minus a. This can be thought of as a shift on the s-axis. Now again, we're not really considering the s-axis as a thing unto itself, but it's a shift on the s side. To prove this, we're going to remind ourselves that by definition 7.1.1 from an earlier set of videos, the Laplace transform of e to the at times f of t is equal to the integral from 0 to infinity of e to the at e to the negative st times f of t dt, where e to the at and f of t are what we're transforming, and e to the negative st is baked into the definition. We can rewrite this integral combining the exponential factors as the integral from 0 to infinity of e to the negative of s minus a times t, factoring out that negative and the t, times f of t dt. Well, this is exactly the Laplace transform of f, but instead of having a negative s up in the exponent, we have an s minus a in the exponent. So that negative of s minus a is playing the role of negative s. A piece of notation that you might see is that the Laplace transform of e to the at times f of t is equal to the Laplace transform of f of t with a little subscript. S becomes s minus a, so a little s arrow s minus a. Once we have a transform, we have an inverse rule as well. The inverse transform of uppercase f of s minus a is equal to e to the at times lowercase f of t. So the e to the at on the t side is related to a shift s minus a on the s side. Let's see how we can use this. We've got the Laplace transform of t to the 10th e to the negative 7t, and as we move on, there are going to be multiple lenses that we can use to look at the functions that we're transforming. And I like to think of it as our expressions now have clues for us. The t to the 10th is the function that we're transforming, because through this lens, what we have is the e to the negative 7t is going to represent the shift. Ordinarily, we would transform t to the 10th and write down 10 factorial divided by s to the n plus 1, and so s to the 11th. But with this e to the negative 7t in there, we now have a shift. And so that denominator becomes s plus 7 to the 11th. This is what it looks like to have f of s minus a. Let's look at the next one. The Laplace transform of e to the negative 2t times the cosine of 4t. I want you to write down what you think that answer is. The function that we're transforming is cosine of 4t, and that transform is s over s squared plus k squared, so s squared plus 16. We have this e to the negative 2t, that's going to give us our shift, and we see that in the denominator, so our denominator is actually s plus 2 quantity squared plus 16, and one thing that a lot of people overlook is all of the instances of s need to be shifted. So this is s plus 2 over the quantity s plus 2 squared plus 16. All of the s's change to this s minus a. Remembering to put this plus 2 in the numerator for the transform of a shifted cosine function is one of the challenges that we face. Another challenge is that we need to remember that that plus 2 would need to be there in order for us to find an inverse transform. We'll see that in a future example. For now, we're now going to transform the inverse Laplace transform of 1 over 2s squared plus 2s plus 5. I want that denominator to have a form that looks like a quantity squared plus a number. And so we're going to think about completing the square, except we aren't going to need to add and subtract like we do in some contexts. 1 over s squared plus 2s plus 5 is 1 over s squared plus 2s. The constant that I need in order for that to be a perfect square trinomial is 1. And so I'm actually going to split the 5 into 1 plus 4. We end up with the inverse Laplace transform of 1 over s plus 1, the quantity squared, plus 4. Because the numerator is a constant, we know that we are going to shift to the sign, also because in the denominator we have a plus. And then we can identify that since we have s plus 1, the quantity squared, plus 4, that k is equal to 2. So we need to multiply numerator and denominator by 2, and then apply the inverse transform. We get 1/2. The shift of s plus 1 is going to give us e to the negative t. And then because the overall function is the transform of a sine, it is the sine of 2t. Next up, we've got the inverse Laplace transform of s plus 1, the quantity squared in the numerator, s plus 2, the quantity to the 4th power in the denominator. There's no way to deal with the s plus 1 quantity squared in the numerator other than to expand it out. So inverse Laplace transform, s squared plus 2s plus 1. That s plus 2 to the 4th power in the denominator, with all those terms in the numerator, doesn't give us really anything nice. We have a denominator that factors, and so we need to use partial fraction decomposition. S squared plus 2s plus 1 over s plus 2, the quantity to the 4th power. It's going to turn into 4 fractions. A denominator of s plus 2, a denominator of s plus 2, the quantity squared, a denominator of s plus 2, the quantity cubed, and a denominator of s plus 2 to the 4th power. Remember, that's how we treat repeated factors in a denominator in partial fraction decomposition. One point of confusion that I'd like to address is that all of our denominators, even though some of them have exponents different from 1, have linear bases. That is, s plus 2, the quantity cubed, has a base of s plus 2. That's linear. Linear factors get constant numerators. And so our fractions are a over s plus 2 plus b over s plus 2, the quantity squared, plus c over s plus 2, the quantity cubed, plus d over s plus 2, the quantity to the 4th power. Clearing fractions will give us s squared plus 2s plus 1 is equal to, now the common denominator is s plus 2 to the 4th power. The fraction involving a already has one factor of s plus 2 in the denominator, so it needs to be augmented with 3 factors of s plus 2. So a s plus 2 cubed, likewise b s plus 2 squared, c times s plus 2, and then d stands alone. We can zero out the terms that have a, b, and c by letting s equal negative 2. If we do let s equal negative 2, it's all instances of s on both sides of the equal sign. And that's going to result in 1 is equal to d. One way to deal with partial fraction decomposition is to expand everything on the right-hand side and then compare coefficients of like terms on the left and on the right. We can also shortcut this a little bit. If we notice we have a times s plus 2, the quantity cubed, that's going to give us an s cubed term. And it will be the only s cubed term we have on the right. There's no s cubed term on the left. And so looking at the s cubed terms, on the left we have 0, on the right we have a, and that tells us that a is equal to 0. Since a is 0 and d is 1, and we've got the constant term on the left is 1 also, we can put that information together and rewrite our equation. S squared plus 2s is equal to b times the quantity of s plus 2 squared plus c times the quantity of s plus 2, remembering that d is 1. We can also record that a is 0. We'll need all that later. I can't use the technique I did before of zeroing out using s equals negative 2, because that would zero out both terms on the right, and frankly, on the left as well. Instead, I'll note that on the left, we have one term that's got s squared. It's got a coefficient of 1. And on the right, we'll end up with one term that has an s squared. It's got a coefficient of b. That's going to tell us that b is equal to 1. Now I'm going to look at the constant terms. On the left, the constant term is 0. All we have is s squared plus 2s. On the right, if we were to expand s plus 2 the quantity squared, multiply it by b, we would have 4b, and then distributing c into s plus 2 would give me 2c. Since we know that b is 1, that gives us that c is negative 2. This isn't really a general approach, but I'm just showing you how you can kind of identify how to find our constants. Now what we have is the inverse Laplace transform of what had started out s plus 1 the quantity squared over s plus 2 to the 4th power is now equal to a over s plus 2, but a was 0, b over s plus 2 the quantity squared, and so on and so on. So this becomes the inverse Laplace transform of 1 over s plus 2 the quantity squared minus 2 over s plus 2 quantity to the 3rd power plus 1 over s plus 2 that quantity to the 4th power. Since we have this s plus 2 as a base in all of the denominators, we see that's our shift. That's going to give us an e to the negative 2t in our inverse transform for every term. In the first term, we have 1 over s plus 2 the quantity squared. So I'm thinking about how would I inverse transform 1 over s squared? Well, that would inverse transform to t. We also have that factor of e to the negative 2t. What would be the transform of negative 2 over s cubed? Well, that's going to give us a t, and that exponent is an n plus 1. So n is equal to 2. In the numerator, we have 2 factorial, and so that is going to transform to negative t squared. And again, we have that factor of e to the negative 2t. For the 1 over s plus 2, the quantity to the 4th power, we see that n is equal to 3. So we need to multiply and divide by 3 factorial. So we end up with 1/6 that would transform to t cubed. And yes, we again have e to the negative 2t in that term. An alternative approach would have been to recognize, hey, I've got e to the negative 2t in all the terms. We could have written this in a factored form. I leave that choice to you.